A manager walks into the network room with a simple request. The new app needs 3 servers today, a test copy tomorrow, and a disaster recovery option before the quarter ends. If every request means buying another physical box, finding rack space, adding power, cooling it, cabling it, and waiting on shipping, the network becomes the brake on the business. Virtualization is the escape hatch. Instead of tying one operating system to one physical server, you carve the physical resources into isolated logical systems. The hardware is still real: CPU, RAM, storage, NICs, switch ports, uplinks. But the thing the user sees, a server, a network, a router, or an application environment, can be created, moved, copied, scaled, and isolated in software. Start with virtual machines. A VM is a complete guest computer running on a physical host. It has its own operating system, its own virtual disk, and its own virtual NIC. The layer that makes this possible is the hypervisor, also called the virtual machine monitor. The hypervisor allocates CPU, memory, storage, and network access to each VM, so several guest operating systems can share one physical server without acting like one messy shared machine. There are 2 hypervisor types. Type 1 is bare metal. The hypervisor runs directly on the server hardware. That is the common data center model because there is no general-purpose host OS sitting underneath every VM. VMware ESXi and Microsoft Hyper-V are common examples. Type 2 is hosted. The hypervisor runs as an application on a normal host operating system. VirtualBox and VMware Workstation fit here. Type 2 is easier for labs and personal use, but less efficient for production servers, because the guest VM must go through the host OS to reach hardware. Now think like a network engineer. A VM still needs network access. It does not have a physical NIC, so it uses a virtual NIC. The hypervisor connects those vNICs to a virtual switch. That virtual switch forwards frames between VMs on the same host and out through the physical NICs toward the real network. This is where CCNA details matter. Server-facing switch ports are often trunks, not access ports, because the host may carry VMs from several VLANs at once. That trunk-to-server idea surprises people because most end hosts use access ports. A virtualization host is different. It can contain a web VM in one VLAN, a database VM in another VLAN, and a management VM in a third VLAN, all behind the same physical cable. The virtual switch tags and separates the traffic internally, then the physical switch sees a trunk carrying multiple VLANs. Same cable, separate logical networks. Virtual machines solve the big server problem, but they are not the only option. Containers solve a slightly different problem: how to run applications in isolated packages without booting a full guest OS for every app. A container includes the application and its dependencies, but it shares the host operating system through a container engine such as Docker engine. That makes containers much smaller, faster to start, and more resource efficient than VMs. The trade-off is isolation depth. A VM has a full guest OS boundary, so failures are strongly separated. A container shares the host OS, so it is lighter and faster, but the host OS matters to every container. That is why the practical decision is not VMs are old, containers are new. Use VMs when you need full OS isolation or different operating systems. Use containers when the application can share an OS and you want fast startup, portability, and scale. At large scale, a container orchestrator such as Kubernetes automates deployment, scaling, and recovery. Virtualization also appears inside the network itself. You already know VLANs divide a physical LAN into multiple logical LANs. VRF does the same kind of trick for routing. Virtual routing and forwarding divides one physical router into multiple virtual routers. Each VRF instance has its own routing table, so traffic in one VRF stays isolated from traffic in another. Picture a service provider router connected to 3 customers. All 3 customers use the same private subnet, maybe 192.168.1.0/30. Without VRFs, a router cannot place overlapping subnets on different interfaces in the same routing table. With VRFs, each customer gets a separate routing table, so overlapping IP space is not a conflict. Customer 1 traffic stays in Customer 1 VRF. Customer 2 traffic stays in Customer 2 VRF. The shared provider router acts like several independent routers. For CCNA, you do not need deep MPLS VPN design, but you do need the behavior. VRF segments a router into isolated routing instances. Interfaces are assigned to a VRF. Routes are viewed per VRF with commands like show IP route, VRF name. A normal show IP route only shows the global routing table, so if all interfaces live in VRFs, the global table may look empty. Same router, different routing worlds. All of this sets up cloud computing. Cloud is not magic hardware in the sky. It is a service model built on shared, virtualized resources. Traditional on-prem means the company owns and houses the infrastructure in its own facility. Co-location means the company still owns the servers, but rents space, power, cooling, and physical security in someone else's data center. Cloud goes further. The customer consumes computing resources as services over the network. The NAST cloud definition gives 5 characteristics. On-demand self-service means you can request or remove resources through a portal or API without a human ticket for every change. Broad network access means you reach those services over standard network connections from many device types. Resource pooling means provider resources serve many customers from a shared pool. Rapid elasticity means you can scale up or down quickly. Measured service means usage is tracked and billed, like storage per month or compute per hour. Here is the decision lens. If a retailer needs extra web capacity for holiday traffic, cloud elasticity lets it scale up for the rush and scale down afterward. Without cloud, it may need to buy enough hardware for the peak and let it sit underused the rest of the year. That does not make cloud automatically cheaper in every case, but it explains why flexibility and measured usage are central exam ideas. Cloud service models describe how much the provider handles. SaaS is the most complete. The provider delivers the application, and the user just uses it. Think Microsoft 365, Google Workspace, Slack, Dropbox, or Zoom. PaaS gives developers a managed platform for building and running applications without managing the underlying infrastructure. AWS Lambda, Azure App Service, and Google App Engine are examples. IaaS gives the customer virtualized infrastructure, VMs, storage, and networking. AWS EC2, Azure Virtual Machines, and Google Compute Engine fit here. The control trade-off runs from SaaS to IaaS. SaaS gives the least control, but the least management burden. IaaS gives the most control because you choose operating systems, VM sizes, virtual networks, and application stacks, but you manage more. PaaS sits in the middle. Focus on code and data, while the provider handles most platform plumbing. Deployment models describe who uses the cloud. Public cloud is open to many customers through providers like AWS, Azure, and Google Cloud. Private cloud is reserved for one organization, and it may be on-prem or hosted by a third party. Community cloud is shared by organizations with common requirements. Hybrid cloud combines two or more models, such as a private cloud that bursts into public cloud when demand spikes. So, when you see virtualization and cloud on the CCNA, do not memorize it as a dry list. Ask, what is being separated from the physical hardware? Who controls the layers? And where does the traffic or responsibility boundary sit? VMs virtualize full computers. Containers virtualize application environments. VRFs virtualize routing tables. Cloud wraps virtualized compute, storage, and networking into services, with self-service, pooling, elasticity, and measured usage. Quick recap. Type 1 hypervisors run directly on hardware and dominate server virtualization. Type 2 hypervisors run on a host OS and are common for labs and desktops. VMs use vNICs and virtual switches, often with trunk links to carry multiple VLANs. Containers share a host OS through a container engine, so they are faster and smaller than VMs, but have a different isolation model. VRF creates separate routing tables on one router, allowing overlapping IP space and isolated forwarding. Cloud computing is defined by on-demand self-service, broad network access, resource pooling, rapid elasticity, and measured service. For service models, remember SaaS is the app, PaaS is the app platform, and IaaS is virtual infrastructure. For deployment models, remember public, private, community, and hybrid.